All right. Hello, everybody. Today is our 16th lecture on the differential privacy course. And this is the last lecture that I'm going to be talking about new materials. So we'll continue our discussion on data-dependent differential private algorithm design and with application to machine learning. Like I said, from the next week onwards, so I will still be coming to the lectures. It is optional, but you are encouraged to come with your questions, and if you want to discuss any questions in the homework, and discuss any challenges that you run into in the project, or if you just want to work a little bit more closely on working out the details in your project, feel free to come to the lectures, and people will take turn and will also discuss as a group on specific questions related to differential privacy and more broadly. Yeah, so just feel free to come. These are the next 3 lectures, and in the last day of the lecture, I believe it's a Wednesday. I'll have to double check. So we'll have an extended session and reserved for the mini symposium. So all the project groups will present their work in the last meeting. Yeah, so I'm looking forward to that. And before that, there will be some time allocated to you and for you to work on the project and then come up with a project presentation and so on. Okay, and for those who are yet to submit their scripts, so there's no time limit. Feel free to submit the scripts whenever they are available. And if you're not able to scribe for the lectures that you signed up for, yeah, please also alert me, and then I'll find alternative means to get these notes written down. Okay, so as a quick recap of the last lecture, we talked about data-dependent differentially private algorithms. In the past 2 lectures, we started with the smooth sensitivity, which is to find a smooth upper bound of the local sensitivity and then add noise according to this quantity, so that it's smoothened across the neighboring data set to the point that when you add like a different noise for different data sets, and if the 2 data sets are similar to each other, the amount of noise that you add, I guess the standard deviation of the noise that you add is not going to differ that much. That allows a family of noise distribution to be admissible for this algorithm to achieve epsilon delta differential privacy, and sometimes even pure epsilon differential privacy. Smooth sensitivity is a bit restricted. So we talked about how we can generalize smooth sensitivity and then come up with an alternative approach of getting data-dependent DP algorithm so that it applies more broadly to a wider family of problems. So that's the topic of the last lecture. We talked about 3 technical approaches. The first one is a distance to instability. The second one is a proposed test release, and the third one is to privately release a local sensitivity and then construct a high probability upper bound of the local sensitivity. And after that, we basically take that upper bound and then try adding noise with magnitude proportional to that privately released upper bound. Right. So these are the 3 approaches that we talked about in the last lecture. I'd like to go over them again, like very quickly, to remind you what are the things that we learned, so as to set the foundation for today's lecture. Okay, so we'll start with distance to instability, so which requires us to define this distance to instability function at a given data set X. So this function, like we mess it up a little bit, like in the initial coverage of this this algorithm, because I defined these functions slightly wrongly, but now like these are written down clearly. you can see that there are two different ways of defining these functions that are equivalent. So one says that this is the distance of x to, and this distance is measured in terms of adding or removing individual. Now in the replace one neighboring relationship, these are Hamming distance, but in the like standard definition of differential privacy with add and remove individuals. So this is L1 distance in the histogram representation of the data set, right? So from X to any of other data set X double prime that satisfy this condition. So this is a set of data sets. So I just need to find, so this distance is defined to be the closest data set within this set that is to this data set X. For instance, if X has a neighbor that has a different output value, then this distance is 0. And if yeah, so basically, so this is how far away does X it is the current data set X away from the closest data set that is not stable. That is not absolutely stable. By stability, we mean that your neighbors and yourself, you need to have exactly the same value when you plug this data set to F, right? So you should think about F to be some kind of a robust function that doesn't really change a lot in the local neighborhood of X. So in fact, over here, we require this F to be a constant function in the local neighborhood of X. And the distance to instability mechanism simply add noise to d of x, add Laplace noise to d of x, and then if d hat of x is larger than log 1 over delta over epsilon, so this is the tail bound of the Laplace random variable. If this happens, then return just f of x without adding noise. Otherwise, refuse to answer. Otherwise, just return perp, saying that, well, this query is not stable, so I refuse to answer your question. Okay, so we yeah, messed up this simple proof last time. Even though we fixed it, I think it's better that we cover it again. So basically, in order to prove differential privacy, we need to prove this inequality, this like epsilon delta indistinguishable property for all neighboring data set. So in the distance to instability, we'll just discuss two cases. The first case is that when the two neighboring data set happens to have the same value fx, right? When they do, then yeah, when they do, then all we know is that their distance to instability changes at most 1, right? So this happens universally. Like we don't even need this. But when this is a case, then outputting either f or perp, like the output space. When this happens, the output space is just f of x or perp. Right, and our decision of whether we output perp or whether we output f of x is coming out of this the output of Laplace mechanism. So this is by the post-processing of Laplace mechanism. In this case, it satisfies epsilon 0 indistinguishability, or epsilon the pure differential privacy. And in the second case, when fx and fx prime is not the same. And this implies that the distance to instability of both these two data set is actually 0. Why is that the case? Because if you d of x, then I can find x double prime to be x, to be x prime, and fx is different from f. Then which means that well, the local sensitivity or just it means that x itself is not stable. Therefore, d of x has 0 distance to itself, therefore it is 0. So similarly, when we are considering x prime, then we can use this x to be the x double prime. And that also gives us that x prime is not stable, therefore the distance to stability is 0. So So once we have this, so notice that the distribution is effectively d hat of x is equal to d of x plus Laplace noise. So this is the same 0 plus Laplace noise for both d hat of x and d hat of x prime, right? Which says that like we'll get identical answers under this region of the Laplace mechanism. Yeah, in fact, under this region of Laplace mechanism, and only when this part happens, when we will run into something bad, and this something bad would lead to the identification of whether this is coming from x or whether this is coming from x prime, because fx and f prime, they are different. The point is that this happens with very small probability, so therefore this is a 0 delta dp. And overall, like for some data sets, pair of neighboring data set, we have pure dp. For some other pair of neighboring data set, we have 0 delta dp. So altogether, this is epsilon delta dp. Yeah, I hope this explanation is clearer than what I was able to do last time. And the next mechanism that we consider is a proposed test release. So this is a generalization of the distance to instability approach. We can think about it this way, even though it appeared a lot earlier in the literature. So the idea is that let's first propose a bound beta on the local sensitivity, and then we can privately test it, and we can privately test whether the actual local sensitivity is indeed smaller than this beta. Right, so we tested by introducing this function. So this is a similar function, but now parameterized by this beta parameter. If you choose this beta to be 0, it recovers the same distance to instability function that we defined earlier. But for the more general beta, this means that how close x is to the set of data sets where the local sensitivity is larger than beta. Right, so this requires that in the local neighborhood of x. So not just x itself, but also in the local neighborhood of x, the local sensitivity is smaller than this proposed bound beta on the local sensitivity, right? If the output is perp, if the output is perp, which says that the data set is which says that the data set is like which says that the test fails, then we basically output nothing, like we refuse to answer. Otherwise, we add noise to what we want to release with magnitude proportional to beta. Sorry, with magnitude proportional to beta. Right. So the proof idea is very similar to distance to instability. So I won't go into the details there. Like there's some subtle differences. So first of all, if this local sensitivity of x itself is already larger than beta, then we know that the distance to this beta instability is 0, because x has 0 distance to itself. And then this means that our criteria of this will only fail with probability probability delta. On the other hand, we do not have this d of x prime beta is also equal to 0, right? So we cannot use that 0 delta like differential privacy under this case. On the other hand, like it is still the case that this distance to beta instability function is like 1 insensitive. It has a global sensitivity of 1. Therefore, adding noise to this would ensure that our decision of outputting perp or outputting fx plus this Laplace noise is going to be epsilon differentially private by looking at the decision itself, because it's post-processing of a Laplace mechanism. Therefore, in the case A, they satisfy epsilon delta dp. So why should there be a delta? So in some unlucky event, right, when this test fails, then we are adding only like a Laplace noise with beta over epsilon, which is insufficient for providing the pure dp for this mechanism, right? So therefore we are using a small delta to capture that, and overall in the case A, so this is epsilon delta dp. On the case B, on the case B, so this is a case when the local sensitivity is actually small. Therefore, when the local sensitivity is smaller than beta, and then our differentially privately released test is valid, then this is a composition of a two-step decision rule. First, it's a post-processing of a Laplace mechanism, which gives you pure DP, and the second round is a just privately release of something that is certifiably with local sensitivity bounded by beta, right? So this also gives epsilon delta indistinguishability, epsilon indistinguishability. So overall, this is 2 epsilon 0 dp. So altogether, you get 2 epsilon delta differential privacy. Okay, and one issue with proposed test release is that we do not actually know how to select this beta parameter to begin with. Like how do we do that? How do we know like which beta to use? That's the most appropriate beta. So then the idea is that maybe sometimes the local sensitivity itself is insensitive, and we can just directly privately release the local sensitivity, right? If we can do that, then we can use our private release together with the concentration of the noise that we add to construct a high probability upper bound of this local sensitivity called the delta tilde, and then we can add noise according to this high probability upper bound. So we've shown in the last lecture that this procedure that is slightly easier to use satisfy like 2 epsilon delta differential privacy, right? So it's not always the case that we can easily privately release the local sensitivity, but if we do, then this is an approach that can be substantially more computationally efficient comparing to previous approaches, and it's also like relatively straightforward to internalize what this means, because we want to like privately release and privatize the decision of whether we how much noise that we add, and essentially this is a smoothing over this is a smoothing procedure that makes a local sensitivity smooth out across neighboring data sets. Yeah, if you are marginally at the boundary, then chances are the probability that you actually the probability that you output something like the probability that you add noise according to, because now this is a random variable, right? Now this differentially privately released upper bound, high probability upper bound is a random variable, and the magnitude of this random variable clearly would rely on like what noise that we use and what is the procedure that we use to privately publish this upper bound, right? So one interesting connection is comparing to the smooth sensitivity approach when we use a Laplace log normal. So Laplace log normal adds Laplace noise, X is Laplace noise, and I guess exp some sigma of X of Z, where Z is a Gaussian. So this is saying that the magnitude of the Laplace noise is now like amplified with randomly according to some exponentiated normal distribution. So this is like quite similar to this privately released upper bound of local sensitivity approach, because essentially if you look at the last equation, the amount of noise that you add has a random magnitude, and this random magnitude correspond to this random magnitude as well, and then this X is a corresponding Laplace noise. Okay, so all these approaches has the same underlying idea of somehow smoothing out the local sensitivity to make sure that we do not learn a whole lot from the learn a whole lot from the noise distribution itself on neighboring data sets. Okay, so we'll give this example on output perturbation on differentially private generalized linear model today. So as a quick summary of the last lecture, we talked about various approaches, and here are their pros and cons. So each one of these approaches have increased applicability from top to the bottom, and not strictly increasing, because distance to instability can be used to handle arbitrary queries, but it requires this restrictive in the sense that it requires local sensitivity to be 0 in the neighborhood of X. And PTR, it generalizes this, but it remains restrictive because it requires us to add noise to some numerical pairs, right? And the private bounding, the local sensitivity approach is the most general, and when it is applicable, it can also be like more computationally efficient. Okay, so like these considerations has motivated us to argue that whether there are like similar approaches that allows us to generalize, say, the proposed test release and privately bounding the local sensitivity to beyond the numerical queries and beyond local sensitivity, because local sensitivity is intricately tied to noise adding mechanisms, right? But there are many mechanisms, say Laplace mechanism, objective perturbation, and many other algorithms that we learned that are useful for differentially private machine learning that are not actually simple noise adding mechanisms. For these methods, if we still want to do data-dependent differentially private algorithm design, what can we do? Okay, so that will be the focus of today's lecture. So we will try going beyond the local sensitivity. We'll talk about a concept called per instance differential privacy, and then how we can make use of this to have a systematic recipe that we can write down. And by just following this step by step, like you will be able to derive data-dependent differentially private algorithms that somehow, and it also allows you to discover the interesting properties of the data. So what kind of information that you need to expose in order for your data-dependent algorithm to work. And I'll give some examples of these, and then talk about two particular differentially private machine learning algorithms that are adapting to certain properties of the data set. And then I'll conclude the lecture with some open problems and some good research directions in case you want to look further into this area of differential privacy and differentially private machine learning. Okay, as an example, so let's take a look at the differentially private empirical risk minimization again, and this is something that we are already somewhat familiar with. Since we spent like 5 lectures on this, so the problem is that we want to minimize, say, the sum of these individual loss functions, and these individual loss functions, each one of them is coming from a particular data point, right? So adding or removing data points correspond to adding or removing individual loss functions, and we assume that these loss functions are convex and L-Lipschitz, and say beta smooth. Okay, just so we've worked out that when we are not making any additional assumptions, and the output theta hat equals to arg mean of this, is not stable, right? So the global sensitivity of this theta hat is infinity in general, and in the last part of the lecture, we talked about how we can add additional regularization, right? How we can add additional regularization here so that instead of minimizing this, we minimize the regularized objective function. And this regularized objective function actually gives us a global sensitivity, of theta hat lambda is smaller than L over lambda, right? So this is what we've seen. And now how about local sensitivity, right? So we can so this lemma below characterizes the local sensitivity and the kind of perturbations that you have from one theta to another when you add or remove one individual data point. So let's say that this additional data point that we add is this little L. Is this little L. So by simply Taylor's theorem and by simply doing Taylor's theorems, you can prove that. So this is slightly more general than we need, but everything is equal here. So we can write the exact perturbation in the vector between theta hat to theta hat prime. So theta hat is the arc mean that you get from one arc mean of this, and theta hat prime is the arc mean of this function. So they differ by just adding like one individual data point. So you can show that this has a form of that in some sense generalizes that of linear kind of linear regression. So it depends on the gradient, the individual gradient of this new data point z at the optimal solution theta hat, and also an inverse of an integral of the Hessian matrix. Right, so the integral goes from goes on the line segment from theta hat to theta hat prime, and yeah, and by the intermediate value theorem, so there also exists some other theta tilde on the line segment that you can substitute into this, which gives us the which gives us the inverse of a concrete Hessian matrix over there. But yeah, the point is that so this is completely data dependent because it depends on the entire input data set through this Hessian, and it depends on this individual perturbation through this gradient and Hessian of this individual data point. And we can upper bound this, so under these assumptions above, to show that the local sensitivity of this theta hat, even without adding this additional lambda parameter, but let's add this lambda as a let's add this lambda parameter just for generality. So we can always upper bound this by L over so this is not just L, but actually L at this particular location. L at the one of the two optimal solutions, and over the, I guess, the smallest eigenvalue of the smallest eigenvalue of this Hessian matrix, some Hessian matrix at theta hat at I guess theta tilde. So this is something between theta 1 and theta hat, right? So you can clearly see that this is a matrix inverse and multiply with a vector, and L is an upper bound of the L2 norm of this vector, and then this is the smallest singular value, which when you invert it, it becomes the operator norm of this matrix that you got applied to this vector. Therefore, you can upper bound this. So notice that this upper bound doesn't depend on this individual. It doesn't depend on this individual L, because this Lipschitz constant is what we assume that applies to all individual L, and this lambda mean is the smallest eigenvalue that depends on the data set, that doesn't necessarily depend on this individual data point. And part of it is because this is always positive semi-definite. So adding this is only going to decrease the it's only going to increase the smallest eigenvalue. Therefore, you can drop that and then bound the whole thing with this L over lambda mean. Okay, so how shall we construct like a high probability upper bound of this local sensitivity LS tilde? Okay, so suppose we want to do upward perturbation, but now make it data dependent, so that if locally, yeah, if locally around here, we have a lower bound of the smallest eigenvalue, then we do not actually have to add this additional regularization, right? So we want to make this adaptive choice of whether we need to add this additional regularization or not before we add noise. Right, so we can't directly add noise to the local sensitivity because this lambda mean could very much be close to 0, right? So the perturbation of this can be the perturbation of the local sensitivity itself can be huge. On the other hand, like we can, if we just want to get a general differentially private upper bound, then we can then we can actually add noise to the denominator directly, and this lambda mean this lambda mean of h theta tilde, if like for the moment, let's cheat and assume that we know if it's fixed. If this is fixed, then if this is fixed, then we can then the smallest eigenvalue is actually has a global sensitivity. Has a global sensitivity that is bounded by beta, because this matrix is a summation of Li theta tilde plus this additional L that we add. And by the smoothness property of this problem, then we can simply privately release this lambda mean and then construct a confidence interval, right? So if this confidence interval is bounded away from 0, then we have a valid upper bound of this local sensitivity, right? Which we can then plug into the previous recipe and then add noise accordingly. But if this is a the confidence interval actually covers 0, then we know that we cannot rule out the possibility that at this like nearly optimal solution theta tilde, like we cannot really bound the local sensitivity that much. And in this case, like we can make use of this information to adaptively elect to add additional regularization to this problem. Right, so we can decide on how much regularization to add based on our privately released lower bound of the stability of the optimal solution. Right, so in terms of how we can get this information out while not having access to theta tilde, because theta tilde obviously depend on the data. So that's somewhat more technical. But for specific cases such as differentially private to linear regression, this Hessian matrix of theta hat is equal to Hessian matrix of theta hat prime is equal to Hessian matrix of theta tilde, and all of them is equal to just this matrix X transpose X, right? So in this case, we can just directly release the smallest eigenvalue of the covariant unnormalized covariance matrix, and that gives us a fully adaptive algorithm that can adapt to the well-behavedness of the data set itself. Okay, so now, like I wanted to somehow generalize this this argument and generalize this approach a little bit based on this example, right? So let's consider the more specific problem of differentially private linear regression, right? And the goal is to find theta approximately and differentially privately find theta that minimizes this ordinary least square objective. since this can be unstable, and sometimes like we want to add this additional regularization, which makes it a ridge regression problem, but we want to approximate this original, this original least square optimization problem when we do not have this additional regularization, right? So the one particular mechanism that we talked about earlier from Minami et al. Is to introduce this additional regularization and then also scale the distribution of this posterior sampling mechanism so this is a mechanism that's parameterized with two hyperparameter, lambda and gamma. And choosing these two hyperparameters appropriately will give you epsilon delta differential privacy. So this is a result of Minami et al. And the question is that how do we do that in a data dependent way, and what are the benefits that we can get out of the approaches of doing things in a data dependent fashion. So one clear reason is that that the reason why Minami et al. Introduced this additional regularization is because they want to make sure that this objective function is strongly convex and this distribution is strongly log concave for any input data set. So even if this data set is X and Y, they're empty set, and even if this X and Y, they are arbitrarily singular, then you still want that strong convexity to apply. Right, but in practice, more often than not, our design matrix X is actually quite well conditioned. So the lambda mean of X transpose X can be bounded away from zero. It can actually be very large, and if that's the case, then we'd like to make use of this data dependent property to make the posterior sampling algorithm giving away like more useful information while satisfying the same epsilon delta requirement on the differential privacy. Because otherwise, being conservative will kill the utility that makes the downstream application like suffer. Okay, so clearly this is not a noise adding mechanism, right? So we're sampling from a posterior distribution, and there are two parameters, gamma and lambda. It's not really that we are adding noise according to some sort of local sensitivity. So in particular, we're not deriving the local sensitivity at all. And like, of course, this has an interpretation of something that's similar to noise adding, because you can say that this is effectively sampling from some normal distribution where theta hat is a solution to the ridge regression, and then you're adding noise with magnitude with a covariance proportional to I guess gamma, or 1 over gamma, I guess 1 over gamma X transpose X inverse, X transpose plus lambda inverse, right? So you can interpret this as a particular noise adding mechanism where the covariance matrix also depend on the data, right? But that's very different from just okay, yeah, looks like things are back to normal. So let me restart. It still says 1%. So don't be surprised if it suddenly if my laptop suddenly got shut down again. Well, so all right, so let's continue. So we were explaining the posterior sampling mechanism and how posterior sampling mechanism can benefit from wait, am I recording? Yes, great. Yeah, so we were explaining that how the posterior sampling mechanism can benefit from the intrinsic strong convexity that's coming from the data set itself. But this is more complicated than just noise adding with local sensitivity, because we are not deriving the algorithm based on the local sensitivity. So there is a noise adding, a data dependent noise adding interpretation for this, precisely because this is linear regression. But but it is a distribution, and that depends jointly on the data and the hyperparameters of this mechanism. And over here, choosing this hyperparameter lambda and gamma according to some predefined privacy budget is non-trivial. Like, it becomes even more challenging if we want to adapt to property of the data set, right? And the question is how can we do it? All right, guys. Sorry again. I hope this time it works out. Like, it's not 5% battery. It's well above the 1% failure. Yeah, we now have a little bit of error of margin. So let's hope that the lecture is not running into the same hiccup again. So I was explaining the posterior sampling mechanism and how it is not a noise adding mechanism by calibrating a particular noise distribution proportional to the smooth version of local sensitivity or some privately released local sensitivity, but rather something that chooses noise distribution according to the data itself. And this mechanism has two hyperparameters, lambda and gamma. And if we can somehow obtain data dependent quantities, then we might be able to bypass the need to use local sensitivity and then analyze this mechanism directly. Okay, so that's the idea. So the general idea of how this could work is for us to work with a privacy loss random variable directly. So recall that the output space can be arbitrary for DP mechanism, but the space of the privacy loss random variable is always univariate and supported on the real line, right? So for each mechanism of interest, we can work out the privacy loss random variable and then try to construct an upper bound of it, for all neighboring data set. And if there are properties that we can take care of about this particular data set that we're running our algorithms on, that affects the privacy loss random variable, then we can hopefully try privately releasing those information, like, because everything about the privacy property is already encoded in the privacy loss random variable itself, right? So it suffices for us to figure out what privacy loss random variable are for this problem, and then figure out which part of the privacy loss random variables distribution depend on the data. And then if we can publish an upper bound of these data dependent quantities differentially privately, then we should be able to construct a high probability upper bound of the privacy loss random variable, and then calibrate the noise and the mechanism specific hyperparameters to the privacy budget that we're given by whoever owns the data. Okay, so in order to talk about this idea formally, so let's take a little detour and talk about the per instance differential privacy. So what is per instance differential privacy? It's a refined definition of differential privacy itself. So instead of requiring that this inequality to be true for all neighboring data sets Z and Z prime, and in this case Z and Z adding one individual, or if you flip it around, so this is Z concatenate with this little z, and the alternative data set would be this Z itself with this additional data point Z little z removed. Okay, so epsilon delta per instance differential privacy specific for one fixed pair of neighboring data set, like just requires the epsilon delta indistinguishability to apply for this one specific pair of neighboring data set, rather than requiring it to hold for all neighboring data set. And this is useful because it measures the precise privacy loss for each individual. Like when a fixed data set, either Z or Z concatenated with Z, is being processed by this randomized procedure and this randomized algorithm A. And we can really think about, for instance, differential privacy to in a similar lens of data of a mechanism-specific analysis, right? So in mechanism-specific analysis, we can think about it as a epsilon as a function of delta for all delta, or the range EDP parameter as a function of order for all order. So here we're just parameterizing this privacy loss parameter as a function of all possible neighboring pair, and we wanted to get instead of just a single number summary, we would like to get a function where we can plug in like the specific pair of neighboring data set, and you could potentially return different numbers. So sometimes it's as big as the worst case upper bound, and in other cases it could be orders of magnitude smaller. Right. So for instance, differential privacy satisfy many of the standard properties of differential privacy, such as composition and closure to post-processing and so on. And we can, it's strictly more general than the standard epsilon delta differential privacy, because we can obtain the standard DP parameter by maximizing over the two neighboring pair of data sets afterwards. Okay, so just to illustrate the, for instance, differential privacy versus the worst case DP for a little bit. So we consider this output perturbation mechanism that we talked about earlier, right? So for linear regression, and we know that we can practically release the smallest eigenvalue, and then this output perturbation effectively add noise that are isotropic Gaussian to the ridge regression solution, right? So if we do that, and if we calculate the per instance DP that's specific for every individual in the data set, and each one of them will give me a number epsilon, and then compute for all of them. So now I have n epsilons, and then the histogram on the left-hand side gives you the distribution of these per instance DP parameters. So this says that for a large majority of these individuals, for this particular algorithm that adds this much noise, and their privacy parameters is actually 2 orders of magnitude smaller than the worst case upper bound that you use to calibrate noise to privacy. And the reason is really that this X transpose X is now like very well conditioned, and because of that, you can take advantage of the data dependent quantity if you do everything right. And the blue line in the middle is what I call the PDP for all. So this is the epsilon Z data set Z and the little individual Z. I max over this little individual Z for all like over the data point universe, right? So this says that this is an upper bound that applies to all individuals, regardless of whether this individual is inside the data set or outside the data set. So even if this is outside the data set, it can be completely adversarially chosen, and this is really a worst case privacy loss that you should have you should have been calibrated your noise, the actual noise that you added to. Yeah, so this is more closely related to DP. And what DP says is that you max over both this individual data point and this data set in this PDP parameter. And this could be completely irrelevant to the current data set that we're operating on, because like this maximization over any data set will end up finding those data sets that are somewhat pathological, with the nearly singular with a nearly singular x, and then you are completely relying on this additional regularization for achieving epsilon delta differential privacy. And beyond linear regression, we can also try bounding the per instance DP losses or like the absolute value of the privacy loss random variable for say the objective perturbation mechanism on logistic regression. So this was from a recent NeurIPS paper. And the exact definition of PDP is slightly different because it's ex post, but I'm not going into the details here. But the gist of these plots is saying that in logistic regression, if your data set, if your data point is being accurately classified with high confidence, then that means that like having you or not having you in the data set will have very little influence to the final logistic regression coefficients that you end up learning. Right, so suppose the final output of the logistic regression classifier gives you something that's nearly perfectly separates these two groups of data points, then the further away that you are from the decision boundary, the more confident the classifier is in classifying your data point, then that implies that your privacy loss is proportionally smaller. Right, so those data points that incur high privacy loss are those that are classified wrongly, and those who are classified wrongly and with high confidence, adding or removing those data points will have a more significant effect that in terms of how they can change the final logistic regression coefficients. Yeah, so everything makes sense, but what we want to focus here is how we can make use of this to design like differentially private algorithms that exploits a data dependent property, but it satisfy the worst case epsilon delta differential privacy parameters that the data analyst would provide ahead of time. Right, so let's go back to linear regression and the posterior sampling. So for the posterior sampling mechanism for linear regression, so I won't go into details, but we can work out that an epsilon delta per instance DP upper bound is given by this like complicated formula. And let me parse this formula for you a little bit. So first of all, this mu is given by this quantity. So it's really the directional, I guess the directional inverse Hessian, or for those who are familiar with regression analysis, this is called the sample leverage score for this data point X. And it could be the in-sample leverage score or out-of-sample leverage score, but it's just taking this inverse Hessian to be a quadratic form. And you can see that if this Hessian goes to 0 quickly, and if X behaves like most data points in the data set, then this value should be very small. It can be as small as 1/n. Okay, so this mu appears in many different places, and over here, and this term is a residual square of the residual. So this says that how accurately the empirical risk minimizer or the ridge regression coefficients is predicting your label based on your data point. If you are predicted accurately, then having you or not having you will not make much of a difference, right? So everything on this expression depend on just these quantities. It depends on this residual, and it depends on this mu. And in order to define in order to use this to design like data dependent DP algorithm that satisfy the worst case DP, the first thing that we need to do is to maximize over this individual Z, over this particular individual, while retaining the dependence on the data set itself, right? So if we do that, then we'll get this expression that eliminates the dependence on this little z, and this little z is little xy. So then not surprisingly, it ends up depending on the smallest eigenvalue of x transpose x, and also on the Lipschitz constant. So the interesting thing for linear regression is that the Lipschitz constant is not actually bounded, right? So how we can make so there are two quantities of interest that are data dependent. One is this L, the other is this lambda mean. And lambda mean is the smallest eigenvalue of x transpose x, and this L is defined over here. L is a function of the norm of this non-private minimizer of this ridge regression. Yeah, with parameter lambda. Right, so this is a data dependent quantity, and this is a data dependent quantity. And in order to design, in order to sanitize the dependence of these epsilon parameter on the data set or the privacy loss random variable on the data set, we need to somehow like review information about x transpose x and the norm of these coefficients. Okay. So as we mentioned earlier, by matrix perturbation theory, so we know that the lambda mean of this minus lambda mean of plus this little perturbation is smaller than is smaller than the two norm or the operator norm of this rank 1 matrix XX transpose, which gives you just something that we can enforce by normalizing the individual data points before we enter them into this algorithm. The corresponding perturbation on the norm is a lot more. It's a lot trickier. So ultimately, what we want is this L. So let me write this down. This L is a quantity that is bounded by the magnitude of the data space. Okay. Multiply with theta hat plus the label space, right? So this is a quantity, data dependent quantity that we want to review, and you rely on this theta hat, and so the natural idea is that can we just directly release this norm of this theta hat? So with the lemma that we like written previously, so we have the exact calculation for this theta hat minus theta hat prime, and then we can write it down, and this becomes just this expression. So we can further bound this expression. We can further bound this expression by just if we say that just use a simpler notation, and x is smaller than alpha and y is always smaller than x smaller than beta and y is always smaller than alpha. Then we can just bound this with alpha plus beta theta norm multiply with so this is a square root, so we have beta over lambda mean plus lambda. Right, so there's a -2 here, right? There's a -2 over here, so this is the expression. But the thing is that the right-hand side also depends on theta hat, right? So this is not a quantity that satisfies local sensitivity or global sensitivity. So the trick that we can use is to somehow convert it into something that satisfies local sensitivity. So satisfy a good global sensitivity bound. and this is a useful trick to learn. So what we can do is to I guess just take the inequality, and then what we can do is to take this inequality and then rewrite it a little bit by multiplying beta and then add and subtract alpha. So we can get alpha plus beta theta hat minus alpha plus beta theta hat prime. So by applying the above inequality, we can get, since we multiplied beta, so we now have beta square. Right, and adding and subtracting alpha doesn't make a difference, and so this is one of the direction. And similarly, we can center around theta hat prime, and then get alpha plus beta theta hat prime minus alpha plus beta theta hat being smaller than beta square lambda mean plus lambda alpha plus beta theta hat prime. Right. So for each one of these, we can basically divide both sides by we can move this negative term to the right hand side, and then combine these coefficients with this beta square over lambda mean, which and then we can take logarithm on both sides. So what we will get is the log of alpha plus beta theta I guess minus over alpha plus beta theta hat prime. So this is smaller than log of 1 plus beta square lambda mean plus lambda, right? So from the first inequality, so this is what we have. So what does the left hand side mean? So this is the difference in the log of the quantity that we actually want, right? Of this quantity that we actually want. And what this is saying is that for any neighboring data set, the right hand side now is a constant. Like provided that we can privately release lambda mean, and then the right hand side is a constant that we can leverage to add noise to the by privately releasing this local sensitivity according to this lambda mean, which is something that we can privately publish because this has bounded sensitivity, and then we can release a log of this scale parameter of interest. So even though we cannot directly release this theta hat, but we can release a transformation of this, right? So sometimes like this kind of trick can be used. And then once we release that upper bound, we can exponentiate it, and that gives us some upper bound of the quantity of interest in the result of this posterior sampling. Right. So yeah, I hope that this illustrates the idea of the data dependent analysis for a posterior sampling in the linear regression, and this is one particular example of the so-called generalized proposed test release approach that we can use to design a differentially private algorithm based on, for instance, differential privacy bound. Yeah, a lot of this is still ongoing work, but you can instead of proposing some upper bound beta of the instead of proposing some upper bound beta of the local sensitivity, you can just propose some fixed parameter of interest. So in the previous example, this is the gamma and lambda parameter from the posterior sampling algorithm, and for the output perturbation, it is a sigma and gamma, sigma and lambda parameter. So these are the groups of hyperparameters, and I'm grouping them together and call them phi, right? So we propose this. We believe this is something that's going to work, and the privacy loss random variable, or the PDP function epsilon will also depend on the data set, right? Will only also depend on the data set. And then the idea is that we propose this phi, and then we work out the PDP, and then we try to privately test if this PDP for all is smaller than a predefined budget epsilon. If so, then this implies that this private test would imply that this hyperparameter choice phi is valid, and then we can go on and run this mechanism with this hyperparameter choice phi. Otherwise, that we've checked that this hyperparameter choice is not good, and we'll just decline to execute it. Okay, so this is in the same flavor of proposed test release. So in proposed test release, you propose beta, you test if beta is larger, if beta is larger than the local sensitivity on your particular data set. And lastly, if the test is successful, then you add noise. Add noise using this beta as a surrogate of the local sensitivity. So over here, this is similar, yeah, except that we generalize it a little bit, which in the last round, we can use any mechanism of interest that's parameterized by some parameter. And instead of proposing this upper bound of the local sensitivity, now we're just proposing some desired parameter of interest. Okay, of course, the same issue about the proposed test release applies here. So sometimes we do not know what hyperparameter to choose in order to give us this predefined epsilon. So it's like shooting in the dark. So I have all these hyperparameters, and we don't know how to choose them. And each one of them will give us some like privacy parameter epsilon, but we don't know what, right? And in this case, how do we run the how do we run the privacy test is an alternative problem. It's another problem that depends on like how sensitive this epsilon parameter is, and how this PDP upper bound epsilon parameter depend on the data dependent quantity over there. Okay, so a slightly different approach would be to say that, let's say that we fix this parameter phi, and then we work out this PDP function. We take the max to eliminate the variable, and so that this upper bound applies to all individuals. But now this still depends on the data set, and then we can release a high probability data dependent upper bound that is parameterized by phi. So notice that this is a function of phi, and we're simultaneously privately releasing the entire function of this that depends on phi. Right? If we can do this, then we can solve the inverse of this function to try to find the corresponding phi parameter that can be used to achieve a predefined privacy budget. Right? So whether you are able to release a high probability data dependent upper bound of this quantity for all phi parameters at the same time will really depend on the problem. But like in the linear regression case, so what we did is essentially this. So we release this L parameter, we release this lambda mean parameter, and these two parameterizes this upper bound, and then we can then once these two are there, we can choose this lambda and gamma parameter in any way we want, and then that will allow us to calibrate noise to a predefined privacy budget. Okay, so you can think about this as a generalization to the approach of privately releasing the local sensitivity. Right, so instead of privately releasing the local sensitivity, now we are privately releasing the like a data dependent upper bound that we can substitute any parameter phi. Okay, so as a checkpoint, so far we talked about two new approaches, like without giving any proofs, because it's still mostly ongoing work. the generalized is the standard proposed test release framework that allows us to apply them to an arbitrary randomized mechanisms. And by working out the per instance differential privacy, working out an upper bound of the privacy loss random variable, that allows us to identify what are these data dependent quantities that we can use to do this kind of calculation and algorithm design. And it relies on either a private test that check whether the outcome is larger or smaller than the predefined budget, or it rely on some approaches to privately publish this data-dependent privacy loss, so that we can sanitize it and smooth it, and then use that to calibrate noise to the privacy requirement with a little bit of overhead. Okay, so it's 2:22. We'll take a 5 minutes break, and when you come back, we'll talk about like two like somewhat more recent examples on data adaptive differentially private machine learning with noisy SGD and under the knowledge transfer framework on the private aggregation of teacher examples. Okay, I'll see you guys in 2:27. All right, we'll resume the lecture. So in the remaining 20 minutes today, so we'll talk about two representative methods in data adaptive differentially private machine learning, and both of them apply to differentially private deep learning. Okay, so the first that we'll introduce the adaptive clipping approach in noisy SGD. So this is one way to adapt to particular structure of the data. So first of all, as a reminder, so how does noisy SGD work? So in every iteration, noisy SGD first sample a mini batch using Poisson sampling with a parameter gamma. So this chooses to include any individual in the data point in the data set with probability gamma independently. And the second, you update your parameter by moving a little bit towards the negative gradient direction. And the negative gradient is now mini batch I. The negative gradient is now perturbed by a Gaussian noise, so that you apply a Gaussian mechanism. So altogether, this is subsampled Gaussian mechanism. So Li theta t, and then right. So following the notation in our in the notebook in the question 4 of the lecture, the question 4 of the homework. So we'll be adding noise proportional to this sigma square tau square, where tau is a clipping ratio. And why should tau be there? Because we're going to be multiplying the minimum of tau over the norm theta t and 1. Right. So if the magnitude of the gradient is smaller than tau, then I'm not doing anything. But if the magnitude of the gradient is larger than tau, then I'm clipping it to something that has exactly magnitude tau. So this ensures that the summation has bounded global sensitivity, and then I'm just adding noise to that and use Gaussian mechanism to release the stochastic gradient in every iteration. Okay, so one challenge in this problem, in this algorithm, is that how do we choose this tau parameter so as to minimize error, right? And also the choice of this tau parameter might not be it might not be good to stick to a constant tau parameter throughout the training. So maybe at the beginning, when the gradients are all relatively large, then we should choose this tau parameter to be larger, so that we're capturing all those information from individual data points. And later in the training, when most of the data points are actually predicted accurately already, then we should perhaps choose this tau to be a much smaller error, to be a much smaller value, so that we can more aggressively truncate this gradient, because we know that they're already very small, right? So that's the underlying idea, and like the ideal sequence of this tau parameter would really depend on the particular rollout of the noisy SGD. So therefore, it depends on the particular data set. Okay, so how do we choose this sequence of tau parameter? So noisy gradient with adaptive clipping, would say that, so I'm gonna choose this tau 1, tau 2 to tau t by looking into the actual data, by privately releasing some information from the data set, right? So the goal that they want to achieve is that they want to choose this tau such that say the kind of a particular percentile of the gradient is reviewed, right? So let's say that we have the gradient norm of all these individual data points being evolving as we keep optimizing this objective function, and then the ideal choice of tau would be choosing tau t to be the, say, 90% quantile of this set of gradient L1 theta t to gradient Ln theta t. Yeah, it's all too normal. Right? So we've learned something that can allow us to do this, right? So what is it? We can use smooth sensitivity, right? So quantile is similar to median, right? So if we try to use smooth sensitivity to release a quantile, then that allows us to privately look into this and then release a quantity by adding a little bit of additional overhead to the training procedure, right? So this could be one of the baseline approaches. What they propose is slightly more elaborate. So they use an online learning approach, which does not require you to access all individual data points in every iteration, because that's computationally prohibitive. And since you are sampling just a mini batch, then you don't necessarily know everything. But still, that you can convert the problem of minimizing of finding the right 19% percentile to be an online optimization problem. And in every iteration, you basically update the parameter of that online optimization problem by releasing some one-dimensional quantity. And since what you release is one dimension, it doesn't really cost too much comparing to what you're already costing by releasing this d-dimensional object over here by releasing the gradient. Right, so that's the idea, and then this paper was I think posted in 2019, but recently published at NeurIPS. Yeah, so it's one way to make noisy SGD significantly more practical. So here are some of their experimental results. So we can see that on many like standard data sets in computer vision and in this NLP data set as well, you can see that when you like in the vertical axis for these two, these are the accuracy. So the higher the better. So comparing to not clipping at all, which is the last column, you can see that choosing you can see that choosing the gamma is the parameter of their online algorithm to select these adaptively chosen threshold tau t. You can see that in many data sets that the improvement can be quite substantial comparing to not clipping at all. Like in some data set, it requires you to do a more like aggressive clipping. In some other data set, it requires you to do less aggressive clipping. But in many data sets, like this actually leads to improvement. For this EM-NIST AE, so this one is the lower the better. So you can see that comparing to the no clip baseline, right? So this the improved performance is like 5-6% in the mean square error. Okay, so going data adaptive. So even though it costs a little bit more privacy budget, it could end up paying off in terms of getting substantially stronger utility. Right. The second algorithm that I'm gonna go over with a little bit more details is Pate. So we talked about Pate a little bit. So this is a so-called private aggregation of t-training examples, and the key idea is that we want to partition the private dataset into k disjoint parts and train one classifier on each split, and then we use this ensemble of k classifier to privately label through majority voting and noise adding some available public unlabeled data set. Right? And then afterwards, we'll have the fully labeled public data, and then we can just train a student classifier on this pseudo labeled public data. Yeah, so this is the last algorithm we talked about in the differentially private machine learning chapter of the course. And the standard PATI, and especially the one that worked reasonably well in practice, just use a standard Gaussian mechanism. So for every individual public data set, you get the teachers voting, you add noise to that, and that gives you the pseudo labels. So standard Gaussian mechanism, it works, but it doesn't scale very well with the number of data points that you need to label. Right? The more data points you need to label, and then the larger amount of noise that you need to add for each data point, and then you are getting a substantially less accurate answer to every data point. A viable alternative like goes data dependent. So instead of using just a Gaussian mechanism to release, you can use this idea with both components are things that we have already learned. So we've learned the sparse vector technique from a long time ago, and it's a sequential composition of the above average. So I don't know if you still remember what sparse vector technique is, but basically you have some threshold you want to identify within a sequence of query, like which query actually has values that are above a threshold, right? Before you run into something that's above threshold, then you're not paying anything, but you just keep giving away a sequence of perps, and once you once you get something that's above average, then you return top and then you restart. So that's above average. And the nice thing about the sparse vector technique is that you can release many bits of information while only paying for that information with a single unit of privacy budget. Right? So PATI with sparse vector technique and distance instability is a combination of the standard sparse vector technique with distance to instability. So the idea is the following. So we have some predefined threshold, and this threshold is applied to how much how many more votes that the largest and the winner category that based on the teacher's voting score is comparing to the second largest. So that's what I mean by the margin. So if the margin is larger than the noise threshold, so this in the above threshold algorithm, I use it to like let's say that the negative margin is above that threshold in the above threshold algorithm, but over here, like the sign doesn't matter. So if this condition is true, when we add when this condition is true, then we're just gonna continue, right? But before continue, we can actually release the exact value of the argmax without adding any noise, right? So I'll tell you why this is possible. And otherwise, then otherwise this means that we will release top. So this is in this case we'll release perp, and in this case we'll release top. And when we release top, then we don't like return anything, but then just we need to update the threshold choice. So suppose we run into this top only a small number of times, then to say it differently, suppose the margins of all the labels that are coming from the teacher votes are sufficiently large, then we can afford to label exponentially more public data points comparing to suppose we just use standard Gaussian mechanism and add noise to every one of them. Okay, so now let me tell you like how this could work. So if we ignore this line and then think about the rest of the algorithm, so this is exactly a sparse vector technique. Okay, and now like suppose we combine this line and this noise adding, suppose we compare this line and this noise adding, this part. If we group these together, then you can then notice that this margin is a surrogate for distance to instability, because if the margin is large, it means that the current data set is giving me something that's far away from being unstable. I need to change like the output of many teachers in order for me to in order for me to change the argmax of the voting score, right? So the margin is large, and margin is a surrogate of the distance to instability. And adding noise to the threshold, if we move this to adding noise to the threshold, if we move this to the other side, is equivalent to adding noise to the distance to instability, right? So if we look at this part of the algorithm intuitively, it's exactly distance to instability. Yeah, we're effectively sharing the noise and sharing the noise adding to the threshold somehow. Yeah, in fact, this needs to be a margin plus noise in SVT. So both the threshold and the actual query needs to be perturbed. Yeah, but we're just like sharing this part of this part of the algorithm and then apply this distance to instability and SVT together, and that gives us something that can release the exact value of the pseudo label, the teacher vote whenever there are high margin. So it turns out that this leads to substantially better algorithms that we can use to analyze Pate, and yeah, I don't know if I have a figure to show, but theoretically it improves the rate from 1 over n epsilon to the power of 2/3 to 1 over n epsilon, right? So now you need substantially a smaller data set to learn a hypothesis class. Like interestingly, there are two other ways of adapting to large margins in Pate, like without using this fancier differentially private approaches like sparse vector technique. So in particular, we can just use the standard Gaussian mechanism, but work with then try to privately release the data dependent privacy losses. So this was from the second Pate paper by Nicholas Peppernot and co-authors. So theorem 6 says it's a RAIN EDP calculation. It's a data dependent RAIN EDP calculation that says that this mechanism that add noise to the voting score and then release the argmax, right? So this procedure, it actually satisfies a stronger RAIN EDP guarantee when we condition on a particular data set and whenever the margin is large. So this informal statement says that if there exists an output that is somewhat overwhelmingly, that happens with overwhelmingly large probability, then under this case, we can show that the data dependent RAIN EDP parameters is exponentially smaller, according to how close that you are to 1. So when this Q tilde when this Q tilde is arbitrarily close to 0, it means that the mechanism on this data set will almost always output I star, right? So you can apply this to the large margin case. So you can imagine that suppose the voting score looks like this, right? Then you are only adding this much of noise to every coordinates. Then with high probability, with a overwhelmingly high probability, this column will be chosen as the argmax, right? Because Gaussian tail like decays very quickly, and the number of votes here can be relatively large. And using this, if there are large margins, so you can fix the algorithm to be just Gaussian mechanism and use this approach to show that the privacy loss is actually a lot smaller. Right, so this is a flip side of the data dependent analysis. Instead of calibrating the noise and trying to achieve some predefined budget, you can show that the actually incurred the privacy loss is substantially smaller. And then you can think about how to privately release this number so that you can make it make it stable. Yeah, so interestingly, there's one last technique of adapting to this large margin that doesn't use any of these, right? So you don't have to use the data-dependent DP analysis, nor using fancier algorithm like sparse vector technique and distance to instability. You can simply use the naive algorithm of the Gaussian mechanism, and then use like other methods, say active learning, to select which data point is worth labeling. It turns out that active learning selects a very similar criteria based on the margin. So active learning select all those data points that will contribute to the learning process. If it helps learning, then I'm getting a label. Otherwise, I'm not. And in the good situations, when there are large margins, and active learning will only select a very small set of data points to label, and that gives you the same learning outcome, right? So we've developed this and showed that theoretically it gives you about the same rate of 1 over n epsilon rather than 1 over n epsilon to the power of 2/3. And in the experiments, we can also demonstrate that so anything with an A is active learning based stuff, and we can demonstrate in the experiments that it also outperforms the passive learning approach that tries to label everything or just label a random subset. Okay, to conclude, so there is an expanding list of papers on data-dependent DP analysis for various algorithms ranging from clustering, statistical estimation, and inference, and topic models like LDA and so on, and boosting and ADA boost and decision trees and XG boost and so on. And many of these are like very hot topics in the recent machine learning and security literature. I just heard like in CCS this year, like one of the differential privacy paper got the best paper award. And before that, the Abadi et al., so that deep learning with differential privacy paper, I think it is by now the most cited paper in for the entire history of the security conference CCS, right? So it's something that's really gaining momentum. And if you're interested in continuing with what you have learned in this course and do some research on it, and here are some suggestions. So coming up with stronger and more practical algorithms and more data adaptive algorithms. So these seems to be a good recipe. And I guess combining the data dependent analysis with mechanism specific analysis, right? So doing the Renyi differential privacy or concentrated differential privacy for methods like proposed test release. And then these are like still pretty open, and there are many opportunities here to improve your DP algorithm. And using differential privacy in new contexts. So in this course, I mostly focus on differential privacy on its own. But the idea of differential privacy and the implication of differential privacy can be used to, say, prevent implicit overfitting, and can be used to prevent p-hacking in science. It can be used to ensure an individual notion of fairness, and for people to design algorithm that in a game theoretics and strategic environment to promote truthfulness and in the data that they submit to the data collector. So DP could also be used as a general smoothing trick that induces stability, that allows learning in contexts where the standard techniques like uniform convergence fails, right? So there are many like novel usage of differential privacy and the related idea, and I hope like this course have covered all the elements like for you to consider and think about, and it gives you an entry point to any of these subsequent areas that builds on top of differential privacy. And lastly, like as DP, like I want to reemphasize this, as differential privacy is now becoming a more practical technology, and many companies are adopting differential privacy. So all the tech companies are adopting differential privacy in one of their products and services, and there will be a need of practical people who know how to use DP tools and how to implement differential private algorithm correctly for each application separately. So you don't have to necessarily invent new DP algorithm, but just applying existing DP tools correctly to solve real life problems. So that could be good research directions. Okay, so with that, I'll conclude. And yeah, I run over time for a bit, but there were some technical issues. Yeah, hopefully I'll see many of you guys again next Monday and next Wednesday, because I will be hosting project consultations and homework consultations for the two lectures next week. So we'll think about what we do for the lecture the week after. But Wednesday, the week after next week, will be our project presentation. So yeah, please work towards that. Thank you all for your interest and attention throughout the course. All right.